Hello, everybody. Hello, and thank you all for taking the time to join us today. It's a great pleasure to see everybody online here, and thank you so much for your time today and for taking the time out to join us on this webinar today. Thank you very much. My name is Alex. I am the publisher of the Journal of Physics Materials at IOP Publishing, and this this webinar is to introduce the launch of a focus issue, a collection of papers in JPhys Materials, and entitled Women's Perspective in Quantum Materials. So we are super excited about this. We think it's a lovely initiative, and we're very much looking forward to sharing some thoughts and the research updates from some of the contributors of this issue in the next hour or so. So thank you again for joining. I have just a couple of very quick housekeeping points before we start. The first is that there'll be, just following these introductions, there will be 6 presentations. So we have 6 speakers, each speaking for around about 8 minutes or so. And then there will be a question and answer session to follow that. So there won't be questions after each talk. We will have a short Q&A at the end and after the last presenter has finished their talk. So if you would like to put any questions into the chat, so ask the presenters anything or comment on any of the talks, then there is a little text box in the bottom right-hand corner of the screen where you can see a URL to something called Slido where you can post your questions. So please do go ahead and post those, and we will be monitoring those in real time throughout the webinar. And we, as mentioned, we'll have a short Q&A, so we would either answer your questions in real time and on the call today, on the webinar today, or if not, we will take those offline and we'll answer them by email and when the webinar is concluded. So one of those 2 things. And my last little housekeeping point is just to say that if you have any queries regarding the journal or the issue more specifically, then please do send me an email. I'll leave my email address on the last slide that we're presenting today that will be on view during the question and answer. So please do email me about any journal queries, and I'll get back to you after the webinar is finished. So I'm just going to say, so thank you again for joining this webinar to announce the launch of this focus issue, this women's perspective in quantum materials. So really happy about this. The issue is now open for submissions, and we're going to publish the papers in it throughout next year, so throughout 2022. And delighted to say that we have over 30 people agreed to contribute their research to the issue already. So that's a wonderful thing. So lots of contributors, and really delighted actually to say that 6 of those contributors are on the call today, on this webinar today, to present their work. So that's what you will be presented with over the next hour. We have 3 editors for the issue, so 3 guest editors who have really been instrumental in putting the issue together, in guiding it, putting together the scope and so on, and what we concentrate on in the issue. And that's Leni, Hae-Young, and Maya. And 2 of those editors, Leni and Hae-Young, are on the call here to host this webinar today. So super thanks to them for that. So on that moment, actually, Leni, I'm going to pass to you, if I may, to introduce yourself, if you may. Thank you very much. Thank you.
Okay, well, so thanks, Alex, for the introduction to the webinar, and thanks to the Journal of Physics Materials for hosting the initiative to launch this perspective on quantum materials, and of course for inviting me to be a guest editor. Well, my name is Leni Bascones, and I'm a theorist on condensed matter at the Instituto de Ciencia de Materiales de Madrid. This is a research institute belonging to CSIC, which is our national research center in Spain. I'm working on quantum materials. I started working on mesoscopic physics, and but in the last 2 decades, I have mostly worked on strongly correlated electron systems, and primarily high TC superconductors, and first cuprates and then overall iron superconductors. And in the last years, I have mostly work on more heterostructures like Swiss bilayer graphene and or ABC trilayers Mores. Well, in these systems, I have studied different problems like magnetic or nematic phases or modes and Hood metal physics or spectroscopic properties. And well, I'm very happy with this focus issue and with the interest that it's creating and the number of researchers that we already have confirmed, because I think that it will help visualize the work of many female researchers. So, well, thanks again to all the contributors and to all the people who is now here at the webinar, and of course to our panelists. Thank you.
Thank you so much. That's lovely. Thank you. And Hae-Young, I'm going to ask you to introduce yourself to introduce Maya also, and the first three speakers, if you may. Thank you very much. Thank you.
Yeah, sure. Thanks, Alex. Hi, everyone. My name is Hae-Young Ki. I'm working at the University of Toronto in Canada. So it's I really appreciate those contributors who has agreed to contribute to do this excellent journal, which I believe will make us some, hopefully initiative to more of these types of research. I specialize in quantum materials, like Leni has speak about. So I'm also working on strongly correlated systems, including high temperature superconductors and quantum spin liquid in magnetic systems. So those has been my recent interest. I think that's it about me. I will also speak Maya, who is missing. We have another guest editor, Maya Vernori at Max Planck for the chemical physics of solid in Germany. She's missing, but she's been also part of the editor board members. So hopefully that we will meet her at some point in future. Okay, so I think we can move on now. So Alex, if you put another slide. Yes, so we have 6 speakers today. I have a privilege to introduce 3 of them, and I will say their names as my best. Hopefully I won't make a mistake, but if I do, please do apologize. Please do excuse me. I have different backgrounds, so it's hard to pronounce, but I practiced with Leni beforehand. So let's see. So our first speaker is Amalia Colvia from University of Oxford. And I won't read your title. Hopefully you can do so yourself, given the time of interest. And our second speaker will be Mariona Coll from Institute of Material Science at Barcelona. And then our third speaker of the first 3 will be Paula Giraldo-Gallo from University of Andes. Yeah, hopefully I did it right. Okay, so maybe we can start.
Thank you. Thank you. So we'll pass over to you to start us off, if that's okay.
Well, good afternoon, and thank you, the organizer. Thank you, IOP Publishing, for this great opportunity to give us a chance to talk about our science, in particular from the women's perspective. In my talk today, I'm going to briefly give you an overview of unconventional superconductivity aspects we study in the class of ion-based superconductors. I'm Amalia Colvia, based at the University of Oxford, and our science relies on funding from EPSRC, Center for Applied Superconductivity in Oxford, collaboration with different high magnetic fields laboratory and diamond line source. So what is the questions we are currently working on? We are trying to understand the unconventional superconductivity in different classes of ion-based superconductor. And on this slide, I have the case of one of the simple structure, which is made of ions, selenium ions. In these materials, we have conducting plate of ions and we link them together chemically with other atoms above the plane. And that structural configuration then creates unusual electronic behavior and unusual electronic maps, which are this kind of Fermi surfaces. And in superconductivity, we are trying to understand what leads to the pairing of electrons. And when we look at a Fermi surface like this, as complex as it is, this will be hole-like carriers, this will be electron carriers. We're trying to work out if the pairing occurs between electrons on the same Fermi surface or between electrons between different Fermi surfaces. This type of superconductors, like many other quantum materials, have extremely complex phase diagram. This is a phase diagram, a three-dimensional phase diagram. Along the vertical axis, we have temperature, and then we have substitution, chemical substitution, either with sulfur instead of selenium or tellurium instead of selenium. And then we have another tuning parameter like applied pressure. And by tuning across various in various directions, we try to work out why these superconducting phases, which are the pink phases here, occur, and why sometimes they get enhanced and sometimes they get suppressed. Another thing we are looking at is why certain phases of matter, like nematic electronic phases, of spin density phases, help or hinder superconductivity. So these are kind of the big questions we're trying to address. In particular, what are the details of the electronic structure of the superconductors that lead to pairing? Then what is the behavior inside the different normal state before the superconductivity emerges? And which are the competing phases with superconductivity? And these ion chalcogenides are a new exciting platform to explore superconductivity, because not only we can explore them in bulk single crystals, but also now they have a huge ability to be tunable. And we know we have in a monolayer case on a strontium titanate, the superconductivity of iron selenium becomes extremely large, close to 100 Kelvin. Some of the reports are around 75 Kelvin. So this extremely high two-dimensional superconductivity is very exciting with potential applications. And also these ion chalcogenides can be made into devices. And in certain composition, they are predicted to show topological behavior with having Dirac-like dispersion on the surface state. And this type of effects could have application in quantum computation. So in our group, we are looking at understanding the electronic behavior of this material by performing a complete studies using a combinations of techniques. So we use high magnetic fields to probe quantum oscillations at extremely low temperatures. We are using angular result photoemission spectroscopy to see the full maps of these electronic phases. And we also perform band structure calculation using V2K to look at what the theory predicts before we do the experiments, and then compare with the experiments. These experiments are performed at different facilities, up to 90 Tesla, and in very extreme conditions, and also using synchrotron light at the diamond light source. And these experiments also allow us to tune superconductivity. And this is a little animation of how a superconducting gap opens up at the Fermi level by in situ potassium dosing of an iron selenium material. Another type of experiments that we do in our research is using extreme conditions of high magnetic fields and high pressure to tune the different competing interaction. For example, in the phase diagram on the right, we can tune in with a single sample inside of a pressure cell. This is inside of a piston cell between nematic, superconducting, and spin density wave. And we can explore using quantum oscillation the behavior of electrons in different phases. We use a large range of techniques from transport studies, tunnel diode oscillator studies, torque measurements, and we rely on having extremely high quality single crystal for this quantum phenomena to be observed. And among the recent experiments which show how we can access quantum phenomena under extreme conditions tuned by pressure, these are quantum oscillations on the right. It shows how the amplitude of these oscillations is strongly temperature dependent, and they can only be observed at extremely low temperature, closer to out of space temperatures, so close to 0.3 Kelvin. And with this type of techniques, we can also explore the nature of the quantum critical phases. So with applied pressure, we can tune, for example, nematic electronic phase towards a critical regime. And recently we detected the formation of quantum Griffith phases and very rare nematic islands appearing in the vicinity of this critical regime. From quantum oscillations, we can probe what happens to electrons inside the material and detect their effective masses, which tells us about the effect of electron correlation. These masses are very heavy, for example, inside nematic phases, but they change a lot as superconductivity is changing. And this information are very important to understand the ground state of this material before they start becoming superconducting. So as an example, in a simple metal, we expect the electrons to have an effective mass of 1, but in the presence of electronic correlations, these electrons become quasi-particle, and their heavy mass reflects the cloud of electronic interactions. We recently are tuning superconductivity, this is resistance versus temperature, with applied strain. And under compressive strain in iron selenium, we find that the superconductivity is also enhanced. And this technique now is going to be expanded to angular resolved photo emission under strain to understand how the different bands behave in the presence of applied strain. And from fundamental research, we move towards how we can implement this type of materials also in devices. And because these iron chalcogenides have van der Waals bonds, they can be exfoliated in thin flakes devices. And here we have explored how superconductivity varies with the thickness of the flakes. And we noticed that in a thin flakes, superconductivity is suppressed, as opposed to a monolayer case on a substrate where superconductivity is strongly enhanced. And thinking about application, in our group, we explore also the properties of materials which are relevant for practical application. And we found that this calcium potassium arsenide phosphor arsenide 4 has extremely large upper critical high critical current densities and high upper critical fields close to 100 Tesla, and critical currents, some of the largest reported for an iron-based superconductor, which makes them potential for practical applications. So these measurements are determined from magnetization measurements and upper critical field from transport studies. And obviously, all this research is not just a contribution of a single person, it's the contribution of a large group of people, and I'm grateful to my group and our collaborators for making this possible. And the overall aim of our research is to try to find that room temperature superconductor and to build up a quantum materials genome. I think by exploring the periodic table and being able to create new materials in different conditions and combine with a full understanding of their properties, we can devise models, and then we can develop new materials for practical applications. Thank you very much.
Thank you so much, Amalia. That's wonderful. Thank you. Really, really appreciate that. Thank you. And we're going to pass to Mariona now. Mariona to give this second presentation. Thanks again, Amalia. Thank you.
Hi, good afternoon, everyone. Let me see. Okay, well, I'm really flattered to be part of this webinar, and of course, I would like to thank you, the organizers and the editors of this special issue, to having me in. So again, my name is Mariona Coll. I'm a research scientist at the Institute of Material Science in Barcelona, and I would like to approach this talk from a synthetic standpoint. So I will start by, okay. So sorry about that. Okay. I would like to start by acknowledging the people of my team, the present and the past members, because of course, without them, it would have been impossible to progress in the field of synthesizing transition metal oxides. So we really like this family of materials because you know that they present a spectacular chemical diversity, and also they present a wide variety of electronic and structural degree of freedom. It's actually the interplay between the spin, charge, orbital, and lattice degree of freedom that can give rise to correlated phases in oxides. And then we can have really interesting properties such as high temperature, superconductivity, or colossal magnetoresistance. But as I said, I would like to focus this talk on the growth and emphasizing the importance of this stage in the research of quantum materials, because the advancement in the growth of transition metal films, heterostructures, prepare artificial interfaces or nanostructure can actually enable the novel phenomena of correlated oxide phases to be controlled at the nanoscale. And actually, this is what holds great potential for quantum technologies. Going back to the growth, I would like to present the way that we try to prepare these materials, the transition metal oxides. And in our group, we have expertise on chemical methods. And these methods are based on metal organic complex, which are a metal atom that is surrounded by an organic shell, let's say. And if we have these complexes in a solution, we call solution processing, that we deposit on a substrate, and then this undergoes a thermal treatment and enables us to control the crystal structure, the phase, and the composition, which actually determines the final properties. We also use atomic layer deposition. In this case, we use metal organic complex in a gas phase. And for a complex oxide, we alternatively pulse these complexes in a vacuum chamber. These metal organic complexes react in a self-limiting manner with our surface, and this enables us to have a nanoscale control in terms of composition and thickness. And what is really interesting is that we can work at very low temperature, which is compatible with CMOS technology. So I tried to summarize the advantages of both techniques highlighted here in green, but also some of the demands that can be interesting to achieve for these correlated oxides. I would like to emphasize the epitaxy and the preparation of complex composition, and of course the potential of atomic layer deposition to prepare ultra-thin films, two-dimensional materials, to have selective deposition and etching, which is actually really important to simplify the lithographic steps that we have right now. And this is quite well established for binary materials, and what we are trying to do in our group is try to achieve this degree of control in complex oxides. So at this stage, you are aware of the relevance of the precursor chemistry. So it's very important what controls the final quality of the film is if we have one metal or two in the complex. If this metal is surrounded only by nitrogen or oxygen and nitrogen, this modifies the reactivity and of course the stoichiometry, the crystallinity, the phase purity. So among the bunch of complex that we investigated in collaboration with the University of Bochum, I selected 4 systems to present you here. And are thin film systems. I will start by the Bismuth Ferrite, which is a multi-ferroic material. We've been able to obtain really nice, highly epitaxial film, meaning that we have a preferred orientation, which strongly determines the properties. We've been able to also develop magnetic materials like this spinel cobalt ferrite at 250 degrees. So again, this is important to be compatible with CMOS technology, is magnetic at room temperature. We also have fine control on the doping of the materials. We've been able to incorporate cobalt in several compositions to tune the photoresponse of multiferroic materials. And this is actually for applications in photovoltaics. Back in 2010, we've also worked in high temperature superconducting nanocomposites. So we embedded nanoparticles in a YBCO matrix, and with this we were able to strongly enhance the pinning force of these materials. We also are active in terms of nanostructures. In particular here, for example, we are able to conformally coat nanotubes, this multiferroic material, on transparent conducting oxides. But focusing on the thin film system, you probably realize that most of them are prepared on a strontium titanate single crystal. This is important to achieve a certain degree of crystalline order, and also allows us to use high temperature treatment to achieve the desired phase. This also has some downsides. These materials are rigid, are expensive, fragile, and somehow limits the application of these materials. So let's imagine that we are able to actually detach these complex oxides from the substrate, which is extremely difficult because the attachment are strong ionic bonds. But let's imagine we can detach it. It will offer many new opportunities to integrate these materials into clothing, flexible polymers, envisaging flexible electronics, integrate it into silicon, create artificial interfaces to investigate novel phenomena. So they open a new arena of research. So we already worked on trying to obtain this, to detach the materials, and we do it by using the sacrificial layer. So on this single crystal substrate, we grow another oxide that enables us to transfer the crystalline order, but then we can selectively remove by common solvents such as water, preserving the integrity of our complex oxide. And then we can freely manipulate this complex oxide and integrate it on many different architectures and arbitrary substrate. So we after a very detailed optimization of this process, we've been able to prepare membranes of binary oxides and also complex oxides. And I will show you here as an example these cobalt ferrite membranes, which are crystalline, as you can see from here, also very smooth. And the fact that we can transfer it on flexible substrates, we can also investigate how, for example, the magnetization varies with the radius of curvature of the polymer. So this is just a snapshot of what we are doing here, but we believe that these chemical techniques and also these transfer approaches offers many new opportunities to prepare complex oxides and design novel architectures, novel heterostructures, and devices that can be useful for quantum technologies. And with this, I will finish my talk, acknowledging again my team, the current collaborators, and the financial support. And thank you for your attention.
Thank you so much, Mariona. Thank you. That's wonderful. Really, really appreciate that, and that lovely presentation. Thank you. Thank you. And next up, Paula. Hi. I hope you can hear me. Hi, Paula. And thank you for joining us. And over to you. Thank you.
It's important to unmute me. So thank you very much for inviting me. I apologize in advance for my voice. I hope it won't be a problem. I have some laryngitis, but hopefully it won't be that bad. So thank you very much for the invitations to the journal and to the editors and to all of you for being here. I want to give you a little overview of some of the things we do in our group. And I'm going to tell you the things we do in the landscape of this title of revealing and optimizing the electronic properties of quantum material. So I lead a group of quantum materials at Universidad de los Andes in Colombia. This is a beautiful picture of my group. Let me put my pointer on. Okay, so this is a beautiful picture of my group with the background of the city of Bogota in Colombia. So let me give you a little geographical a point of view of where we are. So we are in South America, in Colombia, which is the northest country in South America. And Bogota is right in the middle of Colombia. we are unfortunately not surrounded by the Caribbean Sea or Pacific Sea, but it's a pretty beautiful city. And this is the campus of Universidad de los Andes in Bogota, right next to the mountains, where we have a beautiful and very nice air. And the quantum materials lab in physics department is located right next to the mountain, the highest part of the university. So it's really enjoyable to work here. And my group works very nicely following the background, or our spirit, our objectives goes focus on studying electronic phase diagrams of novel quantum materials. So this is an example of one of the materials we are currently studying. I'm going to give you some very recent examples of the things we are doing. So this is the tantalum disulfide material, and we are trying to see how we can strengthen novel quantum phases, like for example superconductivity in this material, in the background of competing electronic phases like the charge density wave in this compound. And we see that we can strengthen, for example, superconductivity by weakening the charge density wave in this material. And no matter the structural phase that we obtain for this compound, superconductivity is optimized. So maybe this is actually related to the sorter. So in order to create these electronic phase diagrams, we put a big effort on synthesizing single crystals of this compound. So these are just a couple of examples of the crystals in the materials we are currently studying. And by optimizing and synthesizing these single crystals, we have the flexibility of actually changing the chemical composition and recreating this phase diagram, like for example, doping with molybdenum these tantalum disulfide crystals. And we complement our efforts by characterizing using generally extreme conditions, like some of you here. And extreme conditions, these are some examples of beautiful magnetoresistant measurements that we have done in this bile semimetal candidate, niobium and tantalum tellurium 4, in which we observe a nice evolution of the magnetoresistance with the dopant, and for magnetic fields that we have available here in the lab up to 15 Tesla. But when 15 Tesla are not enough, we go and use our beautiful contacts and we apply to magnetime in high magnetic field facilities. And we have a lot of experience using the high magnetic field lab in Tallahassee, Florida. So we go there and take beautiful experiments, like for example, in the compound lead telluride, which is a very nice thermoelectric material, very popular thermoelectric, but also superconductor under certain dopings and certain conditions. All right, and we also use a little bit more advanced techniques other than transport measurements like the ones I showed. For example, a resonant ultrasound spectroscopy, in which we measure the mechanical resonant modes of materials. So we put them under some piezoelectric transducers, and we measure the frequencies at which this material resonates, and we are able to obtain those sets of frequencies and therefore extract the elastic constant of this material, which is actually a tensor, which gives us symmetry-specific information on the thermodynamics and the evolution through phase transitions. So I'm going to give you some details on all of this story that I've been talking about. So I'm sorry, my voice is kind of bad. All right. So quantum materials are materials in which strong correlations in the geometry of the wave function makes or leads to a lack of understanding of these compounds under semi-classical models. And under these categories in our group, we study, for example, superconductors in macroscopic condensates. This is an example of the Meissner effect, magnetic materials as well. We are also interested in topological insulators and semi-metals, and in novel insulators such as charge density wave insulators, ferroelectrics or piezoelectric materials. And all of these materials constitute a big promise, as you all might probably know and work on many technological applications like superconductivity and low dissipation transmission lines, or very highly efficient magnetic memories, or even more efficient of these memories using topological insulators and semi-metals, or resistive switches based on this phenomenon, on these novel insulators or magnetic insulator, metal insulators transitions. So in order to study and comprehend these quantum systems, these quantum materials, we know that already these materials have very complex interactions, and there are very subtle forms of emerging electronic properties in these compounds. So in order to simplify this search and this understanding of these compounds, we decided to study these phenomena using single crystals. So for single crystals, you probably know that we can obtain crystals in which the macroscopic shape of these crystals is a reflection of the microscopic unit cell. And in that sense, we can actually obtain very nice information, which is symmetry specific in terms of, for example, important terms in the Hamiltonians that leads to these quantum materials, which are specific to the directions or the bonds or the correlations in different directions of our material. So it is important to not losing this specificity for understanding these ground states. So currently we are studying different compounds. Lately we've been focusing on some transition metal chalcogenides. This is an example of a 2D transition metal dichalcogenide in which we are able to grow and synthesize very nice and large single crystals in which this macroscopic shape is a reflection of these beautiful unit cells that can be exfoliated down to one monolayer. All right, so producing the single crystals and our expertise in producing these single crystals allow us to have the flexibility of varying these electronic properties with chemical doping and optimizing and strengthening some of the noble phases we want to focus on. All right, and we also use extreme conditions in order to characterize these electronic phases in these ground states. So we use low temperatures to reduce the thermal broadening of these electronic states and being able to resolve in full glory their behavior. And we use high magnetic fields to reveal particularly the dynamics of charged particles, which is different and is characteristic of different electronic ground states. So I'm going to show you now some examples of some recent experiments and works we have done using this philosophy that we handle in our group. So the first example I want to show you is the one for the quasi-1D transition metal chalcogenides, which have the general form, the transition metal chalcogenides of the transition metal atoms in the center of this periodic table, and a chalcogen atoms or a certain number of chalcogen atoms. And depending on the number of these chalcogen atoms, we can have two-dimensional materials or quasi-one-dimensional materials. So this low dimensionality comes from the van der Waals interactions among different layers or chains in these compounds, given that we have strong bonds in certain sizes or among certain atoms, and weak van der Waals interaction among others, among the chalcogens. So examples of these quasi-1D transition metal chalcogenides are the family of the tetrachalcogenides, the tantalum, tellurium 4, and niobium, tellurium 4, that I'm going to be talking about. But also we have some trichalcogenides, which has been studied in more detail in the past. So we will focus on the tetrachalcogenide compounds, which form these quasi-1D chains. As you can see here, this is, for example, in the niobium tellurium 4, we have chains of niobium atoms, which are these green ones, surrounded by the squares of tellurium atoms, and these structures form chains which couple weakly by this van der Waals interaction with other chains, forming these quasi-1D structures for this compound. So this compound in this family of compound, the tantalum, tellurium 4, and niobium, tellurium 4, are very interesting because they are candidates to being vile semi-metal or topological materials. And they also are known for a long time for being charged density wave materials as well. And very recently, they have been discovered to be superconductors under high pressure. So these compounds, this family of material, is a very nice playground to study the intersection between these different novel ground states. So we are in the process of studying these compounds. So we have performed some transport measurements for the solid solution of the niobium and tantalum, tellurium 4, seeing a very not a very pronounced evolution in the electronic properties, but more pronounced evolution in features that we observe in these resistivity measurements. This is the derivative of this resistivity, which could indicate an evolution of different transitions to the charge density wave states. So we figured out and we found out that if we want to study the intersection of this novel ground state, we need a very careful and detailed understanding of the basic ground states that we have, for which this family of material has been known for, which is the charge density wave. And we found out that this compound this charge density wave is not very well characterized in this compound, or at least there is no consensus of the charge density wave characteristics. Another very interesting observation that we found is that although the evolution of the resistance measurement is not as marked, the evolution in the magnetoresistivity in the solid solution is very extreme, being of the order of 100% for the niobium tellurium 4 compound, but for the tantalum tellurium 4 is of the order of 1200%, in showing very beautiful quantum oscillations that we don't see for the niobium compound. So we will follow up on this all the fermiology of study of this Fermi surface and their evolution very soon in the magnet lab using Shubnikov-de-Haas measurements. So, because we are not experts in many things, only in very focused experimental techniques, we do the job of convincing people that this problem is actually very interesting and that they allow us or help us understanding this compound on their experimental tools of expertise. So we have a very nice team of Uniandes, which is a mix of theory and experimentalists. We have collaborators in other universities in Colombia, like Universidad Central in STM, and we have collaborators which are doing very nice ARPES measurements in Universidad de Paris, is Andrés Santander Giro, or in Brazil. Also STM collaborators in Spain, at Stanford, and we are performing currently DFT measurements with the help of people here in Colombia and in Belgium. So we have assembled a very nice team of people to go deep into the problem of understanding all these different intersections of these three different novel ground states in this compound. So let me show you some of the beautiful results we have obtained here in the STM perspective, characterizing and directly observing the characteristics of the charge density wave in the niobium tellurium 4. So this is the niobium tellurium 4, this very quasi-1D material, in which the characterization, the direct characterization by STM of the charge density wave formation has been done previously, but not with the resolution of the tools we have currently available experimentally. So we have retaken this problem, and we have observed very beautiful patterns of charge density wave formation for this compound. And we have been able to understand first the superstructure and directly observe for the first time the superstructure formed by the charge density wave formation in this compound, which is this one here, in which you see these very nicely peanut-shaped entities, which are actually formed by tellurium trimers that are observed in the surface of this compound. When you cleave it, it's formed by tellurium atoms, the surface of the compound, which form trimers, and given their zigzag orientation or organization within the surface of the material, and because of these chains, given their quasi-1D character, we can see a superstructure formed by these trimers, which has a periodicity given by this drawing. So we are also able, we are also able to observe the information regarding the vector of the charge density wave in this compound, and the different stacking of the charge density wave formed by not the tellurium trimerization in the surface, but the niobium trimerization, which we are not able to directly observe, but given an asymmetric distribution of the charge density in the tellurium surface, we are able to deduce, and due also to our DFT calculations, that the trimerization and the charge density wave formation is given in the niobium atoms in this compound. And we have an stacking that is very characteristic, which gives the patterns that we see for these superstructures. Please let me know if I'm running short on time.
Sorry, Paula, to interrupt. If you could wrap up in
sure.
a minute, if you could, please. Thank you.
Sure. Sure. Just a couple more slides. And to end up this story on the niobium tellurium 4, not only we were able to observe these superstructures, which are actually commensurate with the lattice parameter of the material forming commensurate charge density wave in this compound, but we are also able to observe that if we take larger scale topographic image, we see defects in this material, which are very extended throughout large distances in our compound. And studying their characteristics, we see that this material is full of domain walls, which form facelifts, walls or domain walls, which makes this material a decommensurate charge density wave instead of just a commensurate charge density wave. So I will leave the story of the resonant ultrasound for a different opportunity because I'm running short on time. But if you are interested in knowing a little bit more about our studies in high cuprates, high temperature superconductors, the cuprate superconductors, in terms of possible electronic nematicity observed in this material, I encourage you to contact me so that we can speak. And with this, thank you very much for the invitation, and we are very happy to collaborate with you. Thank you.
Thank you very much, Paula. Thank you for that. Thank you. I appreciate that. And I'm just going to share my screen. Thank you. So let me just bring that up to now. So Leni, if you're able to just present the next 3 speakers, if you may, please. Thank you very much.
So thank you. So, well, it's my pleasure to introduce the next 3 speakers. Professor Priya Mahadevan, so from Bose National Center for Basic Science in India. Professor Paula Mellado from Adolfo Ibáñez University in Santiago de Chile. And Professor Silke Buhler-Paschen from University of Vienna in Austria. So, well, thank you for being here, and we are looking forward to hearing your talks. So first we start with Priya.
Thank you, Leni.
Sorry.
Yeah. Can you hear me?
Yeah.
Yes.
Okay. At the outset, I'd like to thank all the editors for the opportunity to present some of the work which we've been doing on understanding the twisted bilayers of the transition metal dichalcogenides and really why they deviate from regular semiconductor behavior. These materials have been known for a very, very long time, maybe over 100 years, and they basically are known as, just boring semiconductors, where if you look at them from top, the top view has these atoms arranged in a hexagonal form, and essentially what you have in these, and I'm going to focus my talk on molybdenum diselenide, where you have a central layer of the transition metal atom, and you have a layer of these anions, which are the seleniums above and below. And the local crystal field around this central molybdenum atom gives rise to a lifting of the degeneracy of the d levels. And so essentially, one has a semiconductor just because each molybdenum atom over here has a formal d electron count of 2. And so these levels are filled up. And so if you any band structure calculation with any flavor of exchange correlation functional that you use gives you that it's a semiconductor. It's basically a band insulator, and you have a set of, it's a classic example of a semiconductor. All the interest in these materials have emerged again very recently because these layers, as I said, are coupled. You have these layers of transition metal sandwich between the anion layers, and these you have in any material, what you have is that these sandwiches are coupled to each other by very weak van der Waals interaction. And so this has led to a very cheap epitaxy possible, the van der Waals epitaxy, where even using a small sellotape or a Scotch-Brite, you could pull out one or more layers, and in a controlled manner, you can form heterostructures in any manner. And the advantage over here is that if you took 2 layers of these and rotate them about, and you can form these heterostructures, which are normally not possible, what you do is when you rotate one layer with respect to the other, what you find is unusual physics happening. Of course, These have very large unit cells associated with them. And as a consequence of the large unit cells, one would expect them to have very small Brillouin zones associated with them. And therefore, you would think that they are, essentially very giant molecules with dispersionless levels. And so the correlated phenomena that one sees in some of these, and I'm showing you here the experimental results from the group of Corridine, where they and Abhay Pashupati, where they have taken twisted bilayers of tungsten diselenide. And what you see is that if you took your Fermi level from the top of from the gap region and you're doping holes into the system, what you see in this case is that you see that you go through states which have zero resistance, and then you go into regions which are insulating, and then again zero resistance states. So this seems very surprising because you have, what you'd expect for a typical semiconductor would be that you have a continuum of states. And so this is some of the questions that we've been addressing. How exactly should we think about these materials? Because after all, they're coupled by very weak van der Waals interaction, and you just require a small force exerted by a sellotape or a Scotch-Brite to pull layers apart. And there should be a consequence of this very weak force on the electronic structure. And indeed, when you look at the electronic structure for and plot for a monolayer and a bilayer, which I'm showing you over here, what you would see is that indeed what you see is that they're pretty much similar all over, which suggests that indeed the electronic structure is very weakly perturbed when you have two layers. So why do we see these phenomena which you usually associate with correlated systems in these materials? So before we go on to that, the question we wanted to ask is, why shouldn't we think of these materials as just, look at them as a weak perturbation of the untwisted limit even when we have these very large Moire cells associated with these rotated structures? So before we go on to that, one should look at something, the fruit fly essentially of semiconductor physics, which is gallium arsenide. And when you look at, you have a primitive cell, and what you do is you construct a supercell. Indeed, it's the same. There's nothing, you haven't perturbed the system, and yet you see a spaghetti of bands, and there's no resemblance of the wide band gaps, wide bands that you see in the parent compound, which really suggests that we need to do something more if we want to extract it in this limit, extract out the bands. And that's what we do. There could be two ways of doing it. What you do is you have the full-fledged wave function for the supercell, and you project those onto the initial unperturbed states, for instance, and then you recover and you do this analysis at each point, and you see what you do is you recover the initial primitive cell band structure, indeed, because there is no perturbation in this case. However, in the perturbed case, also we carry out the same analysis to see which ones actually emerge from the primitive cell and what are the deviations that one finds. And carrying out this analysis at a reasonably large angle where there is no real, there isn't the unusual correlated or unusual correlated physics that one has seen in the context of WSE2, what we find is that what I'm showing you over here is the result from our analysis where we've projected all the perturbed wave functions onto the unperturbed ones. And that's shown in the green lines over here with the width of each point indicating the weight over there. And the other case, we compare it with the unperturbed limit. And what we find is that we recover the low energy band structure in this case, indicating that the system is very weakly perturbed as one hypothesized, because they are indeed van der Waals materials. So the question is, would this be true for all twist angles? And indeed, what we did was we considered the twist angles in the regime where there was interesting physics, and that is where the experiments have been done in the same regime around 3 degrees and 4 degrees and so on. So I'm just showing you one of the results, where essentially what you see is that we do have a band which emerges out, which is split off from the rest of those dispersing bands, indicating as earlier that most of the electronic structure remains almost unperturbed, whereas there is a split off band. And indeed, if you had your Fermi level here, you would have it to be semiconducting. And then as you pass through these states, you would have it metallic and then again semiconducting. So, well, to conclude, what I would like to say is that what we are doing and our future work is on these twisted bilayers is to start from the untwisted limit and explore perturbations and try to understand what's happening in these systems and construct a picture of each of the electronic structure in each case. So with that, I'd like to conclude, and I'd like to thank the people who've actually done the work. It's been my graduate student who's been involved in this work, Sumanti Patra, and these are some of the publications that have emerged. Thank you.
Thank you so much. Yeah, that's wonderful. I really appreciate that. Thank you very, very much. And passing on to yourself, Paula, next, if possible. Thank you.
Okay. Do you see my screen?
Yes, that's great. Yes, thank you.
So thank you so much for the invitation. Thank you to the organizers and to the editors. So today I will give you a brief survey of some examples of very nice phenomena that arise in magnetic systems. So just an overview of so many opportunities that one can find really a lot of fun here. In insulating quantum magnets, we'll have some long-range quantum entanglement. We'll see fractionalized excitations. Frustrations really plays a crucial role to make things even funnier. We'll find spin excitation that can take the form of monopoles, or some of them can have show topological properties, etc. So many possibilities. Just here a few examples of them. Spin ices with its classical and quantum versions. Quantum speed liquids like the Kitaev model, ferroelectrics, Floquet topological magnets, antiferromagnetic chain insulators, and as was said before, now this twisted bilayer graphene, which offers a new opportunity to observe magnetic transport in these semiconductors. So let me begin with our old Kitaev honeycomb model. And this is a spin model of 1/2 spins that live in the site of a honeycomb lattice, and it's a model that is exactly solvable. The excitations are abelian anions. That's the great things. These abelian anions, right? That they live in 2 dimensions, and they don't have Bose, neither Fermi statistics, but something in between. The Hamiltonian look like what is shown here. You will see exchange interactions that are anisotropic. They depend on the direction of the bond. And the way how to solve this problem is just to fractionalize the spins in terms of 4 Majorana modes. And when you do that, you get an effective Hamiltonian, which is quadratic in the C Majoranas, which live in the sites. So the system has 4 phases at 0 temperature, 1 gapless phase, and 3 phases which are gap. Okay, depending on which is the bond which you are going to have stronger respect to the other 2. And in this gap phase, you can have the lowest energy excitation from the ground state, which is a state that has fluxes equal to 1 in each of the plaquettes, being a plaquette an hexagon. The lower energy excitations are vortices, and these vortices in the gap phase can have 2 flavors, like can be the E or the M vortices, depending on which type of plaquette you are. So the plan here was to add dislocations or lattice defect to this honeycomb lattice in order to realize non-abelian anions. And how we do that, we consider first what happens when you move a vortex, these lower energy excitations along a chain. And these vortices can also move between chains or between plaquettes of the same type. different type means shadow and light, and also moving vertices along in between them. So if you do that, if you allow a vortex to move in a perfect lattice without any defect, they will be always the same type. An E type will be an E type, an M type will be an M type. But if you include these locations, these vortices will change flavor, and that changing of flavor that occurs, which is a unitary transformation in a system which is degenerated, produce non-abelian statistics. So this is the way how we can produce non-abelian annus, just winding vertices around these locations. Another very nice example is taking also the Kitaev model, but now we can add another part like a Heisenberg contribution here. So we have our previous Kitaev model. Now we add a Heisenberg contribution, and we irradiate this system, okay, with a laser. And this, for instance, can be the electric field with some frequency and some phase. And what happened there is that doing that process, the spin is going to couple to the laser electric field through a time-dependent version of the on-off catcher phase. It's essentially the analogous of what happened with electrons in the Peirce phase. But now for spins. So when we do that, we get an effective Hamiltonian now that is different from the previous one in that we have a new piece here, which is a Zeeman type of interaction, which actually depend on the amplitude and the phase of the time varying electric field. And this system is very nice because when you study the properties of the excitation of the magnons of these systems, we get edge states, which are denoted here. So this is the spectrum of the magnons, right? And these are the bulk spectrum, and these the red lines correspond to the chiral edge state that realize under certain circumstances. That means for certain phases and amplitude of the electric of the laser, we will get either a trivial phase in terms of topology or a topological phase, which is depicted here in terms of these edge states. There are other very nice things that can happen just thinking in terms of dipoles, just dipolar interactions, which we know they are anisotropic, they are long range, and you place these dipoles right around chains with some modulation with some amplitude lambda, and you stack many of these chains and you study the magnetic dynamics of these systems. We can find also that the system actually is topological for a certain range of lambda, and we also can see some edge state in a system that seems very simple at the beginning, just because of these dipolar interactions and in the way they are placed here in a lattice, okay? In the regime where there is a high anisotropy along the anisy axis. And finally, we can also find in systems in clusters with dipoles a realization of the magnetoelectric effect, right? In which actually because of the easy plane anisotropy of the dipoles in these clusters, 2 dimensions and 3 dimensions, and because of the nature of the dipolar interactions, right, and the Hamiltonian, typical classical dipolar Hamiltonian can be mapped into an exchange energy term and an antisymmetric exchange term, which this give rise to a Yellochinsky-Moria type of interaction, which explains why actually in this system we were able to find manifestations of polarization under an magnetic field or magnetization under an electric field, which is what we call linear magnetoelectric effect. And with that, I would like to conclude and thank you once again.
Thank you very, very much, Paula. That's great. Thank you. Thank you. I really appreciate that. And the last talk from Silke, if that's okay. Thank you. Thank you for joining us. Thank you.
So do you see my screen? Is it all set?
Yes. Yes, that's great.
Okay.
Yeah.
Okay, thank you very much. Yeah, also let me join in thanking everyone for setting this up. I'm really excited about this format, and I want to give you here a very brief insight into just one aspect of my research about correlation-driven metallic topology. These are the collaborators that have contributed to the small amount of results I'm going to show. And this is my wonderful team in Vienna. So we have people from physics background with chemistry background, and together we span a broad range of expertise from single crystal growth all the way to ultra-low temperature measurements. Maybe even more importantly, we have a common goal, and our goal is to find new land. So how does one do that? Well, usually if you search for something new, it's useful to have a map at hand. Even if it's wrong or incomplete, it can still give some guidance. Like here, obviously, America was missing, but still Columbus found it. So what is it in our case? We are, of course, up to finding new phases in quantum materials. And let me show you how we can proceed to find such maps to understand the systems. Obviously, our playground is the periodic table. You have seen it already several times. It's important for quantum materials to have the materials. And we are interested in particular in strongly correlated quantum materials. And to obtain them, we typically have these elements which are at the brink of bringing localized to itinerant electrons into the system. And that's sometimes very useful. So what we then do, well, we grow different materials, we study them, and we try to create a map. And this map, one example of such a map is shown here. It's a zero temperature phase diagram of antiferromagnetic heavy fermion compounds, just as an example, where what you see here are the different phases that exist, and one tries to sort of find out which theoretical parameters govern this whole system and where you have to look, what you have to do to create certain kind of physics. So for instance, along this brown line here, one has very exciting physics associated with strange metal behavior, unconventional superconductivity, and so on. So what I want to highlight here, however, is something different, something new. Can we find phases based on strongly correlated electron systems that are not governed by broken symmetry, like here, but by non-trivial electronic topology? So what are the knobs, or what are the theoretical parameters that we have to introduce? Well, that can't be answered shortly, but I just show you one example here. So what we found out is that in addition to starting with correlated systems, we need to also take a careful look at symmetry aspects of the system, and ideally have a very strong spin-orbit coupling. So in this material that I'm showing here, cerium-3 bismuth for palladium-3, we have all this. And indeed, we found a very interesting new topological, strongly correlated phase, which we dubbed wild Kondo semi-metal. So let me just highlight one of the exciting properties of this material. And that's shown here. So it has what we call a giant spontaneous Hall effect. So what is that? You take your sample, you feed a current through, like in a normal resistivity measurement, but you don't do anything else. And you measure the transverse voltage, and it is there. Usually you need to apply a magnetic field to the system to have that, but we don't do that. And also the material intrinsically in itself, it is totally non-magnetic. So that is a very amazing effect, that you sort of get deviation of carriers out of nothing, apparently, and it's a giant effect. So in fact, people have an idea where it comes from, and there is a theory that predicts such an effect. So this is the electronic structure of a wire semi-metal, and the Y nodes are known to be sources and sinks of something called the Berry curvature. And that Berry curvature actually has an effect on moving charges as if it were a magnetic field. So you can see that from this equation here, where this is the out of equilibrium distribution function of the electrons just driven by electrical current. So it was predicted to have this effect, but the effect was expected to be extremely small, to the level that it could not be detected. So why we detected it, and the way we understand it is that it is due to the extreme mass renormalization we have in these strongly interacting systems, and the fact that in these systems, the Y node is quite precisely tuned to the Fermi energy, that we can have this very large effect. The second aspect of this strong correlation in this topological system is that the system becomes very tunable. So we needed only a relatively modest field of 9 Tesla to suppress this wild physics altogether. And from the properties we observed, we have to conclude that what we actually do here is to annihilate these Y nodes, which is something quite exciting. We also could figure out which are the adjacent phases to this interesting new topological phase. So to sum up, yes, we have started to discover new land, a wild Kondo semi-metal phase, and we have also started to understand stabilization mechanisms of this phase by driving the system to other phases. So quite in similarity to what was done previously on strongly correlated electronic phases with trivial topology. Of course, there will be many other topological phases beyond a wild Kondo semi-metal. And what really the agenda for the research for us is for the next years is to find out what are the conditions to form what kind of topological strongly correlated phase. And we will hope to find new phases, find new or other extreme topological responses. And of course, there will certainly be new devices coming out of this on the longer run. And with that, I would like to thank you for your attention.
Thank you. Thank you very, very much, Silke. That's wonderful. Really, really appreciate that. Thank you, everybody. Thank you. We are we're running a little bit late, so we're gonna follow the Q&A portion of this webinar. And just to say, if you join the webinar and you're a little bit late doing so or miss some of it, then it will be available as a downloadable piece immediately afterwards, so you can access the full webinar using the link that you signed up to it with, and it will be available there. So again, thank you, everybody. Leni and Hae-Young, just I didn't know if you have any final thoughts before we say goodbye.
Well, I think it has been a very nice set of talks. So I just would like to thank again all the speakers. So we have had quite the variety of topics, and so thank you. Thanks again.
Yeah, I also like to thank to all the speakers. It was really, I really enjoyed all the presentations. I have a few questions, but I don't think we have time to go through, so we may connect in person at some point.
Wonderful, thank you. And yes, thanks again, everybody. It's really lovely hearing about all that's going on. And thank you. That concludes the webinar. And thanks everybody for taking part. And see you all soon. Thank you very much. Thank you.
Thank you. Bye-bye.